everything we do is available on BioniChaos.com. Go check it out, provide your feedback. And the drop down here, you can have neurology, cardio, imaging, vision, hearing. But you also have muscle activity, so EMG. And we have these 3 tools. Some of them don't fit the page very well. Hey, we can fix that, but this one's essentially instead of a button using your mouse cursor. So it's essentially indirect EMG recording, EMG monitoring using a mouse. And that one's actually doing that hand animation where you can actually click on each finger one at a time, see how it affects the EMG, the muscle activation, assuming you have 2 electrodes on the wrist. And nicely, it has a nice demo mode that we just can use, so we don't have to click on it ourselves. Kind of nonsense. He's testing anything ourselves.
Welcome back, everyone. Let's jump straight into this explainer. Today, we're taking a look at a truly fascinating intersection of biology and engineering, decoding EMG signals. We'll discover how the human body's invisible electrical signals are actually captured, measured, and used to power real-world technology. If you've ever wondered how the human nervous system talks to the physical world, you're in exactly the right place.
It sounds a bit like science fiction, right? How exactly does a simple muscle flex manage to control a complex robotic arm? To answer that, we're going to start at the absolute micro level with a single muscle twitch, and then build our way up to advanced human-computer interfaces. By the end, you'll see exactly how biological intent becomes mechanical reality.
Here's our roadmap for today. We'll cover the spark of muscle movement, visualizing your EMG signals, decoding the muscle metrics, and finally, prosthetics and physical rehab. So let's get into it. Section 1. The spark of muscle movement, from brain to brawn. Electromyography, or EMG for short, is how we measure the electrical activity produced by muscles as they contract. Think of your brain as a light switch and your muscle as the bulb. Right before that muscle physically moves, a tiny, invisible spark of electricity travels down the wiring to turn it on. EMG is basically the science of eavesdropping on those sparks. It captures that brief electrical burst right before every physical movement, pulling the invisible into the visible world. Let's break that down. First, your brain sends a signal down your nerves. Second, the muscle gets that signal, contracts, and boom, a physical change happens, like a moving finger. Third, electrodes placed on the skin capture that signal spike. You can actually see this play out perfectly with digital tools like an EMG hand simulator. When you trigger a virtual finger, it mimics this biological sequence. The finger moves on screen, and instantly a simulated electrical waveform spikes in the background. It's a perfect proxy for seeing how movement and data are fundamentally linked. Moving right along to Section 2. Visualizing your EMG signals, seeing the invisible. Now, it gets really interesting when we compare different types of actions. Take a look at a static muscle contraction on the left. This is like holding a heavy textbook completely still in front of you. Your muscles are working hard, giving off a steady, sustained hum of electrical activity. But on the right, we have dynamic signal variations. Think of rapidly typing or wiggling your fingers. The waveform completely changes into wild, erratic spikes. Those visual squiggly lines are literally telling the story of what the muscle is physically doing. It's not just about movement versus stillness, though. It's all about power. Changing your contraction intensity directly alters that visual waveform. Picture yourself making a fist. Now squeeze it harder and harder. Tools that visualize this data show how your flex intensity directly pumps up the amplitude of the visual wave. A light squeeze is just a tiny ripple, but a maximum effort squeeze, that creates a massive, towering spike. The size of the wave is a direct, visual translation of your physical effort. That brings us to Section 3, decoding the muscle metrics, the math behind the muscle. Biomedical engineers need more than just squiggly lines, right? They need hard numbers. We look at specific metrics to assess muscle health and function. First up is peak amplitude, the absolute maximum value. It's kind of like capturing a runner's absolute top sprinting speed in a single second. Then we have the RMS, or root mean square value. This gives us the sustained overall power output over time, more like a runner's average marathon pace. And of course, the mean value is your simple average. Turning a chaotic wave into these precise mathematical metrics is exactly how we gauge how healthy and responsive a muscle truly is. Let's say you see a peak amplitude of 1.5 on a digital dashboard. That's not just a random digit, it's quantitative proof of a heavy flex. While the visual wave flashes by in a fraction of a second, the software locks in that 1.5. That gives engineers a concrete, actionable value that they can use to trigger a specific command in a physical device. Now, you have to remember baseline noise. Think of it like static on a radio. Your body and environment are always producing a little bit of ambient electrical static. As you can see here, increasing your contraction intensity lifts your targeted electrical signal way above that static level. A medium flex definitely stands out, but a maximum flex completely towers over the noise. This is absolutely crucial in engineering. If the computer can't tell the difference between the radio static and the actual muscle flex, the technology just won't work. Let's zoom out a bit for Section 4, Prosthetics and Physical Rehab. Real-world impact. This isn't just theory. This data is actively transforming lives. By decoding EMG signals, medical professionals are diagnosing complex neuromuscular disorders, figuring out exactly where a nerve or muscle is failing. Over in physical rehab, these signals help guide recovery strategies. A doctor can actually see if a recovering muscle is firing correctly on the inside, even if the patient's physical movement is still weak. And then there's the incredible frontier of controlling robotic prosthetic devices. This is where all the pieces come together. EMG translates human intent into robotic action. Think back to our first question about how flex controls a robot. For an amputee using a prosthetic arm, the biology and the math totally merge. The user thinks about flexing their missing hand, the remaining muscles contract, and the electrodes pick up that invisible spark. The software calculates those peak amplitude and RMS values we just talked about, and those hard numbers act as digital commands. They tell the robotic hand exactly when to close and exactly how hard to grip. It's just a brilliant fusion of human biology and computer code. This insight reminds us why mastering these foundational signal processing concepts is so absolutely crucial. By studying EMG signals, professionals can assess muscle health, diagnose disorders, and understand motor control. It really highlights that understanding the difference between a static hold and a dynamic spike, or calculating an RMS value, is the very first step toward building life-changing biomedical tools. You literally have to understand the body's language before you can teach a machine to speak it. We've seen how a tiny biological spark can become a mathematical command to move a robotic limb. So I want to leave you with this final thought. As our sensors become incredibly sensitive and our algorithms become even smarter, how will this intersection of human biology and computer code shape the future of medicine? Keep that question in the back of your mind as you dive deeper into biomechanics. Thanks for joining me for this explainer, and I'll catch you next time.
Okay, so that's notebook LAM. As you can see, we have a mind map. Mind maps actually help. Yeah, that's the mind map. So we have the BioniChaos platform. Biomedical modalities, core technologies, educational tools, philosophy, and outreach. What are the core technologies? Signal processing, artificial intelligence, web development. Eulerian video magnification. Yeah, that's what the tool to monitor your heart rate is using your web camera. Fast Fourier Transform is used everywhere to convert time series to frequency domain. Wavelet denoising is very, very useful. Resampling engines. What's that? Not sure. If you click on it, you get more details. What's on AI? Neural network training, EEG speech decoding, face API, age emotion guessing. Yeah, we made a tool on that as well. Check it out. It should be on the site. Generative versus deterministic AI. Yeah, we have a blog on that. Web development. Yeah, we could mention TensorFlowJS, allowing us supposedly to train and deploy models in the browser. So we do want to look into that. Educational tools, simulation, visual illusions. We can do it. Simulations, prosthetic arm, cochlear implant simulator, ultrasound exploration, gait analysis. Yeah, we have all of those. Go check them on the site. Yeah, doing visual illusions. They are relevant to neuroscience. So we have quite a few out there. Philosophy and outreach. Yeah, that's what we do, trying to democratize data science. Open source is useful. Yeah, so it's quite a useful mind map.